This is the first lesson on matrices. A matrix is simply a rectangular array of numbers. For us, we're going to consider matrices over the real numbers, but equally we could look at matrices over the complex numbers, or indeed any other field of numbers, such as the rational numbers. So matrices are written either in round or square brackets. So here are some examples. I tend to use round brackets, but you can use square brackets if you prefer. And quite often we'll use Roman capital letters such as M and N or A to denote matrices. In the book, these will be in bold, but writing by hand, there's no need to make them bold. And a matrix has dimensions, so the dimensions of a matrix are m by n if it has m rows and n columns. So I'll just highlight the words I'm defining. So we can see, just looking at these examples, here M is a 2 by 2 matrix because there are 2 rows and 2 columns, and the matrix N is a 2 by 3 matrix because there are 2 rows and 3 columns. And a matrix is called square if the number of rows equals the number of columns, so if M is equal to N. And the zero matrix, which is usually 0 underlined or 0 mn if its dimensions are m by n, is the matrix with all entries 0. So, for example, the 2 by 2 zero matrix is 0, 0, 0, 0. The 1 by 3 zero matrix is 0, 0, 0, and so on. So, column vectors are also examples of matrices. So the 4 by 1 matrix with all entry 0 is also a 0 matrix. And the identity matrix denoted IN is the n by n matrix with 1s on the leading diagonal and 0s everywhere else. So what does this look like? Well, I1 is simply the matrix 1. I2 has 1s on the leading diagonal, which goes from top left to bottom right, and 0s everywhere else. I3 has 1s on the leading diagonal and 0s everywhere else. And I4 and I5 and so on are the same. 1s on the leading diagonal, 0s everywhere else. So that's the identity matrix. So we've seen a few different types of matrices here. An important property of the identity matrix is that we'll see later, if the multiplication makes sense, which it will do for other n by n matrices, but depending on whether, if A is, say, m by n, where m is not equal to n, then only one of these is true. Because matrix multiplication isn't always defined, but we'll see later on that if the multiplication makes sense, then multiplying by the identity doesn't change the matrix. That's why it's called the identity matrix. So now we move on to addition. how do we add matrices together? In the way that you think we do, which is simply by component-wise. This happens component-wise. What does this mean? It means if we have two matrices of the same dimension, maybe it's important to say this is only defined for matrices of the same dimensions. So if we have two matrices, well, so if we have something like 2, 1, 0, 4, 3, 6, and then let's take a third, minus 1, minus 1, minus 1, minus 1, minus 1, and we add them together, we do it component-wise. So we take the 2 and the third and add them together to give 7 thirds. We take this 1 and this minus 1 and add them together to get 0. 0 minus 1 makes minus 1. 4 and minus 1 makes 3. 3 and minus 1 makes 2. 6 and minus 1 makes 5. So we just do it in exactly the way you think we would, and same for subtraction. So now on to scalar multiplication. If beta is a real number that's not 0. I don't know if you've seen this notation before. This just means this symbol here is called set minus. So this means not including. So if beta is a real number that isn't 0, and we do beta times a matrix, maybe we'll just say first beta times m. So if beta is a non-zero real number and m is a matrix, beta m is the matrix with all entries of m multiplied by beta. So example, if beta is a half and m is the matrix 4, minus 6, minus 8, 4, then we just multiply all the entries by a half, and we get this. So this is scalar multiplication. Beta is a scalar, and so that works probably in the way that you think it would. So now you can have a go at exercise 6a, and we're only going to do questions 16 and 17. Which involve problem solving using addition, subtraction, scalar multiplication. But because this is quite straightforward, we're going to move straight on to matrix multiplication. So this is slightly more complicated. So first of all, let's let A and B be matrices. And we can only multiply. AB is defined, AB exists, if and only if the number of columns in the matrix A is the same as the number of rows in the matrix B. So let's just think about some examples. So if we had something like A is 1, 2, 3, 4, then we need, in order to multiply, how many columns does A have? It has 2, doesn't it? One column here, another column here. So B has to have 2 rows. And it can have as many columns as we like. Could be something like this. So here's a nice matrix B. And now we can multiply these. We couldn't multiply if B had a different number of rows. So if A is an m by n matrix and B is n by k, that ensures we can multiply because this n, the number of columns of A, is the same as the number of rows of B. Then AB is defined and is an m by k matrix. So here A is 2 by 2 and B is 2 rows by 5 columns. So the answer, well, M is 2, N is 5, so we're expecting the answer, AB, to be a 2 by 5 matrix. But, and we'll explain how to construct that in a moment, but first note that the order of matrix multiplication matters, because can we work out BA? Can we do B times A? Well, B is 2 by 5, it has 5 columns. A is 2 by 2. The number of columns of B is not the same as the number of rows of A. So BA above is not defined. So in general, AB is not equal to BA for matrices. Another way of saying this is to say that matrix multiplication is not commutative. Commutative just means we can commute the matrices. It means that AB is BA. So addition of matrices, for example, is commutative because A plus B is the same as B plus A. So maybe we'll just make a note. In general, commutative, an operation star is commutative if A star B is the same as B star A. Okay, so let's see then examples of how to multiply matrices. Or maybe just first we'll say, but matrix multiplication is firstly associative. This means that A times BC is the same as AB times C. So the order you multiply in, if you have 3 matrices, it doesn't matter which pair you do first. And it's also distributive. And this means, for example, that A times B plus C is AB plus AC. And A plus B times C is AC plus BC. And also if we have a scalar beta outside, that would also be multiplied by everything. Okay, so let's see examples of how to multiply. So we'll start with a 2 by 2 example. If we take the matrices 3, 4, minus 1, 0, and 2, minus 8, 1, 1. And we want to multiply them. In general, for matrices, you don't write something in between when you multiply. The way we do it, so first of all, this is 2 by 2, and this is 2 by 2, so the answer is going to be a 2 by 2 matrix. Now, to get the first entry in the answer, the entry here, this entry in the blue box is in the first row and the first column of the answer. So what we do is we take the first row of the first matrix and the first column of the second matrix. And then we do 3 times 2 plus 4 times 1. So the thing that goes here is this times this plus this times this. This is 3 times 2 plus 4 times 1. Well, that's 6 plus 4, so that's 10. So 10 is the first entry in the answer. The second entry in the answer, in the red box, well, this is in the first row and the second column. So again, we take the first row in the first matrix and the second column in the second matrix. And we do the same thing. We do 3 times minus 8 plus 4 times 1. Well, that's minus 24 add 4, which is minus 20. So minus 20 is the second entry. And then the third entry we'll do in a green box. Well, this is the second row and the first column. So we do the same thing with the second row and the first column. Minus 1 times 2 plus 0 times 1 is minus 2. And then lastly, in yellow, this entry here is in the second row and second column. So we take the second row and the second column, and we do minus 1 times minus 8 plus 0 times 1, which is 8. So we can see the answer is 10 minus 20 minus 2, 8. This procedure can be extended to other kinds of matrices. So we'll see now a different example. If we take, perhaps if we take, let's have A is 1, 1, 1, 0, 1, 3, 0, 0, 1. So that's a 3 by 3 matrix. So in order for the matrix multiplication to be defined, we need that 3, the number of columns, is the number of rows in B, the second matrix. And then we'll take B to be 0, 0, 2, 5, 1, minus 1, 0, 0, 1, 1, 1, 2. So the number of rows in B is the same as the number of columns in A, so we can work out AB, which is the question. And then we're going to do the same procedure. The number of zeros is to make it slightly easier to help us, because a lot of things will be 0. And we know the answer is going to be a 3 by 4 matrix. So to get the first entry, whatever goes in the top left of the answer, whatever goes here, is in the first row and the first column. So we take the first row and the first column, we do 1 times 0, plus 1 times 1, plus 1 times 1. This times this, plus this times this, plus this times this. And we get 2. Moving along, the second entry in the first row, we're still in the first row, so we're still using this, but we're now using this column. So we do 1 times 0, plus 1 times minus 1, plus 1 times 1, which is 0. And then moving along to the third entry in the top column, still using the first row, we're now in the third column, so we do 1 times 2, plus 1 times 0, plus 1 times 1, that's 3. Then the fourth entry over here is in the fourth row this time. Sorry, fourth column this time. So we do 1 times 5 plus 1 times 0 plus 1 times 2, which is 7. Okay, so that's the first row. Then the second row, we now take the second row first column. We do 0 times 0 plus 1 times 1 plus 3 times 1, that's 4. Second row, second column is 0 times 0 plus 1 times minus 1 plus 3 times 1, that's 2. This entry, the next entry is 0 times 2 plus 1 times 0 plus 3 times 1, that's 3. The last entry in the second row is 0 times 5 plus 1 times 0 plus 3 times 2, that's 6. And then final row, we're now using the bottom row, this row here. So to get this entry, we use this row and this column. 0 times 0 plus 0 times 1 plus 1 times 1, that's 1. And then second row, 0 times 0 plus 0 times minus 1 plus 1 times 1 is 1. 0 times 2 plus 0 times 0 plus 1 times 1 is 1. 0 times 5 plus 0 times 0 plus 1 times 2 is 2. So the answer to this multiplication AB is 2, 4, 1, 0, 2, 1, 3, 3, 1, 7, 6, 2. That's the answer. So this procedure can be extended to multiply any m by n matrix by any n by k matrix. And so you might also have to do slightly more complicated questions that sometimes involve, for example, solving simultaneous equations to find certain matrices, or you might have to, you might be asked to work out powers of a matrix, which, so for example, if you're asked to work out a squared, you would just do a times a. If you're asked to do a cubed, you would do a times a times a. If you're asked to do a squared b, you would do a times b times a times a times b. And of course, this would not be the same as something like a cubed b cubed necessarily, because matrix multiplication isn't commutative. I think we'll stop there.